Welcome, everyone. Today we have Joe Kearney from the University of Iowa presenting to us, and I'll hand the floor to Joe to introduce the project and the team.
Thank you, Dawn, and welcome to this April STEM webinar. As Dawn said, I'm Joe Kearney, and I'm at the University of Iowa. I retired a year ago and still hang around and work with the Hank Lab that Jody Plummer and I directed for years. So this work was performed in the Hank Lab, and the lead researcher on this was Jaheen Malik. This was part of her PhD work that she finished up last year. So this work is motivated by an interest in finding ways to use technology to make pedestrians safer on roadways. Over the last 20 years, roadways have become safer for vehicles. Vehicle fatalities have been steadily reduced, but pedestrian fatalities remain persistently high and have been increasing. There are a variety of ways that technology is used to try to improve pedestrian safety. Many of these focus on ways to capture the driver's attention and alert them to vehicles in their vicinity. This includes in-vehicle warning systems and high visibility crosswalks, and also adaptive headlights. These are a new form of headlights that would illuminate pedestrians on or near the side of the roadway. There are also approaches, but many fewer, that have looked at ways to help pedestrians be safer on roadways. So adaptive headlights can also project a message on the road in order to inform pedestrians of dangers of approaching vehicles. There's been a variety of experiments looking at eHMI on autonomous vehicles to try to communicate the intention of the vehicle to the pedestrians. We spent some time looking at ways that new vehicle communication technologies can be used to help pedestrians by providing information on their cell phones. So the vehicles are being equipped with communication that allows them to communicate with other vehicles and with roadway infrastructure. And this offers the potential that they communicate with pedestrians and technology that they have, their mobile technologies, such as a cell phone. So in our first study that was published in 2018, we looked at how so-called vehicle-to-pedestrian communication could be used to send alerts and warnings to texting pedestrians to tell them when it was either safe or is unsafe to cross a road that was filled with traffic. We later went on to look at how augmented reality could be used in order to put these warnings embedded into the gaps themselves, using really a simulation of augmented reality. This first study was done in our large screen simulator, that so-called cave simulator that had, it has 12-foot long walls and 8-foot high screens, and then a 10-foot wide screen in the front. So the viewer is immersed in roadway environment. And what we did was use virtual reality to create simulated augmented reality in which there would be signals that would be embedded in the traffic to show when there were gaps between cars that were safe to cross, illustrated by the green arrow there, and when there were gaps that were unsafe to cross, which is by that circular, red circular signal. And what we found was that those who had the alerts were more discriminating in making their gap choices. They were less likely to take small gaps, and they were more likely to take large gaps than participants who did not have the AR alerts. So that gives us some indication that this information is useful to pedestrians and can help them make safer decisions in crossing traffic. So then this comes to this study, which was looking at augmented reality to help pedestrians make the difficult decision of how to cross two-way traffic. So we have when you have two-way traffic in with opposing lanes, the pedestrian has to make judgments about when two approaching gaps between cars are going to align sufficiently that they can cross them and get across the road safely. So this study we couldn't do in our large screen simulator because the simulator was not long enough for us to walk through 2 lanes of traffic. So instead, we used the MetaQuest Pro head-mounted display system and conducted the study there in head-mounted display virtual environment. I should say, if anybody has any questions along the way, just unmute and ask questions, and then we'll also have a time for questions at the end. So in our virtual environment, we simulated AR so that we put bars of translucent bars of light above the cars that indicated when gaps were crossable. And pairs of gaps coming in opposite directions had similar color bars when the gaps were jointly crossable. So on the left here, you see the control condition. On the right, you see the alert condition. And this is a signal, those 2 blue bars that are illuminated above the vehicles and signal that there was a safe gap here that the pedestrian could cross to get across the road. So those bars indicate crossability of pairs of gaps. And as you're looking down the road, you can look to the left down there. You can see an oncoming gap on the right-hand side, and there'll be a similarly oncoming gap on the opposite direction, so that it signals that those gaps, when they arrive, will be crossable together. So let me show you a video of this. Now, this is a replay of a simulation trial. And so there's 2 panels here. On the top panel, it's kind of a close-in view of the participant. The participant's head is represented by that white sphere. And then there's a cone coming out of the pedestrian's head and a longish nose that represents the direction they're looking, where their head is facing. And then on the bottom, we have a larger overhead view that you can get a bigger window to see cars approaching. So now let's start the video, and hopefully you can see this video moving. And what I want you to do is notice the gaze direction of the participant. They look to the left and then to the right. So they're scanning the environment, looking for approaching gaps in 2 directions. And here comes one in blue, and there's 2 gaps in the left and right-hand lane, both of which have these blue bars that signal they could have crossed there. Now they chose not to, and now they're waiting. You can see they look to the left and to the right, trying to match up gaps. And now there's an orange one coming. They look back and forth and then cross the road and get to the other side. So that's a typical trial for this experiment. We had 2 conditions. There were roughly 30 participants in each of those conditions. The control condition, they had no bars to indicate crossability. And in the AR condition, they had these bars that indicated crossability. Now, of course, in the real world, we project that they would have AR glasses on, and those AR glasses would then project those bars into the real environment. Those glasses don't exist yet, so we're simulating that here to say, if you had those, how would that help you cross roads more safely? So how did we measure the crossability of a gap? So here's a depiction of 2 gaps, one in the near lane approaching from the left, and one in the far lane approaching to the right. So you'll see, you can see my cursor, right? Yeah, okay, so there's this yellow car here that's the lead car in the near lane. There's the tail car in the near lane, Here's the lead car in the far lane and the tail car in the near lane. Now, as these cars move forward, these two gaps will have an opening where you can get through both gaps, and potentially that would be a crossable gap. So how do we measure the crossability of this gap? One of the ways to look at the affordance of a gap pair is this time graph down here. This time graph represents when a participant would have an opportunity to cross in this dynamic situation. So this is a static representation of the dynamic trial here. And so down here, what we see is each of these bars here represents when a vehicle was in front of the pedestrian. So first the yellow vehicle passes the pedestrian, then the blue vehicle passes, then the green vehicle here passes, and then the red vehicle. And then the time between is the gap between these cars when there's an opportunity for the participant to cross through this gap. And as you can see in this one, they could begin to cross as soon as the yellow car passes them. And then as time moves on, they can cross over here through the second gap in the far lane. This particular gap is sometimes called a rolling gap. That's because the gap opens in the near lane first, and they can enter before the far lane gap even opens. And then if they wait the appropriate amount of time, they can then cross into the far lane and finish crossing. So we identified 4 attributes of gap that determine the crossability of the gap. There's the size of the near lane, because they have to get across the near lane. There's the time available in the far lane, and we measure that as the effective far lane gap. It's the part of the far lane gap that can be reached once the yellow car is passed. So if I move that purple car earlier in time, you can see there's a portion of the gap here they couldn't reach if they waited until the yellow car passed. So the effective far lane gap in this situation begins as soon as the yellow car passes and ends when the tail car in the far lane passes. The third attribute is the total gap size. This is the time between when they can enter the near lane and when they have to exit the far lane. Here again, if I push that purple car forward, the total gap size doesn't change. It's determined by the near lane and the far lane. Lead car in the near lane and tail car in the far lane. And lastly, there's the temporal overlap. They have to be able to get from the near lane to the far lane. So there has to be an overlap that allows them to make the transition from the near lane to the far lane. So these 4 attributes, we determine thresholds for these 4 attributes and to measure the crossability. And as long as the gap meets all of those thresholds, we judge the gap to be crossable and put in an AR signal to identify in both of those gaps that those gaps are jointly crossable. You can cross that gap pair. So now here, using my very sophisticated animation system, I'll show you a crossing. Here is the time. In purple here, we see the time available for crossing, and I'm just going to step through the crossing. Here, our pedestrian is moving, the cars are moving, time moves on, and here they exit. So now I'll go backwards, move them back again, and just animate that one more time. Lead car in the near lane is passed. They enter the road, cross the near lane, go between the 2 lanes, cross the far lane, and they're out. So we ran our experiment using this AR system and compared AR participants with participants who had no AR system, the control participants. And what we found is that the AR participants were very compliant with the AR alerts. When the AR participants received an alert, they crossed the gap pair 92% of the time. When they saw a gap that was not alerted, they only crossed 7% of the time. In contrast, the control participants crossed gaps that would have been alerted had they been in the AR condition 68% of the time, much less frequently than did the AR participants. And they were more likely to cross the unalerted gaps. One of the best ways to look at the effect of these gaps is to look at ambiguous gaps. These are the gaps that are crossable, but only barely crossable or modestly crossable. So here is a graph that shows the likelihood of crossing for both alerted gaps and unalerted gaps for the control condition and the alert condition. So this is based on the overlap between the gaps. When the overlap was very small, none of the gaps were alerted. When the overlap was very large, all of the gaps were alerted. When the gaps were small, very few people crossed, only a few in the dashed line here is the control condition. You see the control was more likely to cross unalerted gaps and less likely to cross alerted gaps, particularly in these ambiguous gaps that have overlaps of 4 and 5 seconds. So those are pretty tight gaps. And you can see here there are substantial differences in the groups. Overall, we found there was a significant difference between the groups in both the likelihood of taking gaps that were alerted and the likelihood of taking gaps that were unalerted. AR participants were more likely to take alerted gaps and less likely to take unalerted gaps. The other thing that's interesting to look at is where they spent their time. If you remember that video, you could see them looking to the left, looking to the right. There's a lot of head turning that goes on in order to check approaching gaps to see if they're going to align. And so this is a graph that shows where their head was oriented. 0 here represents when they entered the road. And so you can see before they entered, they spent most of their time looking at the near lane in both the control condition and in the alert condition, although those in the alert condition looked more towards their left in the near lane than those in the control condition. There were also checks to the right to look in the far lane here, and that's the dark purple. So before they cross, they look more to the left. And then just before they begin to cross, they do a quick check to the right, and that's what this peak here is. And then they predominantly look ahead once they start crossing, sometimes with a check to the right. But once they enter the road, they rarely look to the left and mostly look straight ahead to see where they're going, or look to the right to check the oncoming car in the far lane. So the differences here are, you see more looking to the left, more focused on the left in the AR condition in the near lane. And they do a bigger check to the right. So there's a more dramatic check to the right just before they go. We also saw that overall there were fewer head turns in the alert condition than there were in the control condition. They're more focused on looking for the approaching alert and then checking to the right to see the other matching alert. What did participants have to say about this experience? Participants had higher performance and lower frustration scores on the NASA TLX survey. They perceived physical demand was higher with the alerts. 85% found the alerts to be helpful, and 70% said they would trust them. But there was some concern about over-reliance on the alerts. We've seen this with technology before in our cell phone studies, but there's some wariness that if you get too dependent on technology, you may leave yourself exposed to technological failures and have problems because of that. So AR alerts were, participants were significantly more likely than control participants to cross alerted gaps and not cross unalerted gaps. Participants were highly compliant with the alerts and found them helpful and trusted them. And participants made fewer head turns in the AR condition. Among the things to watch out for in the future are AR alerts must be designed for different abilities, particularly people with different vision abilities. This is a very vision focused assistance system. But you have to think about people with different color abilities, different color perception, and making this salient for them as well, and for people who have low vision. AR is still very challenging in the real world. This is would be quite challenging to do on AR systems as they exist now. Over-reliance on technology may be dangerous, but finally, AR offers potential to aid in street crossing decisions, and is worthwhile to investigate in the future as the technology develops. Lastly, I want to thank the Hank team. There's a large team we have here, and it's a very collaborative environment, and lots of them were involved in the study. So thanks to all of them. And thanks to Safer for the sponsorship to make this research possible. Okay, happy to take questions.
Joe, there's one question from the beginning of your presentation in the chat. I'll just read it to you. Are pedestrians being killed by the proliferation of supersized trucks? Hang on, it scrolled. Supersized trucks that have come to the market in the past 6 to 8 years. And then there's a second one.
Yeah, that is a serious problem, supersized trucks, partly because they tend to hit the pedestrian at a higher place. So they're more massive, so that's a problem. But they also have a higher point of connection, and so they hit the pedestrian more likely up in the chest or head area. Mm-hmm. So that's certainly part of the problem. You know, I think it's not totally clear. I think during the pandemic, people were driving faster. And so I think vehicle speeds are potentially part of the problem. There's more and more moves to different road infrastructures, including roundabouts, and roundabouts can be challenging for pedestrians. So I don't think it's totally clear what all the issues are that cause the increase in pedestrian deaths. At any rate, it's clearly in everybody's interest to find ways to make roads safer for pedestrians, especially at times when they're particularly vulnerable, either in periods of high traffic or nighttime or at non-signalized intersections.
Thank you. And then there is another comment that says 3 questions, no need to answer them all in a row or all of them if there are other questions. So the first question is, how does variability in pedestrian crossing speed affect the notification?
So yes, in this one, we did not take into account variability of pedestrian walking behaviors. We have done studies in the past where we looked at older pedestrians, and we did an adaptive system that would judge their crossing speed and adjust the notifications so that it adapted to their crossing speed. In this experiment, the participants were all young adults, and so they were all very able, and so there wouldn't have been much adjustment that would have been necessary, but it's certainly possible if you created such a system to make it adaptive to the pedestrian's walking speed and mobility.
Did any of the simulations result in a vehicle pedestrian crash?
I think we had no crashes in this one. We rarely have crashes in these simulations. It does happen periodically, and mostly it's a clip of the heels when they get across the intersection. So we haven't, and of course, because it's simulation, when there is a crash, there's no injury that happens as a result of it.
Okay. And then the final of the 3, what is the liability?
Well, I think this is an issue that I think I'm not equipped to answer. I think you need to talk to somebody who is more familiar with the law than me. I think anytime you have warning systems, this is, I mean, it has to be true for warning systems in cars too. So anything that tells you, instructs you one way or another, has potential to cause problems. And I don't think I can tell you the legality or the, who would be responsible in the event of a collision or worse yet, a death.
Yeah.
Our interest is in saying, okay, let's look at these kinds of technologies and in a safe environment to say, how can they possibly influence behavior and how can they potentially make roads safer?
Okay. That participant said, thank you so much. Then we have another question. What differences have you seen in AR technology in rural environments compared to more densely urbanized areas?
Say that again, Don.
Okay. What differences have you seen with AR technology in rural environments compared to more densely urbanized areas?
Yeah, that's interesting. These are all good questions. To the best of my knowledge, there aren't studies that look at AR. AR is so much in its infancy, and particularly AR in real world environments. Most of the AR works best in indoor environments and in reasonably small closed environments. And so I don't know that there have been any studies looking at particularly outdoor AR and comparing it urban to rural environments. One of the problems in the urban environment is just the amount of clutter that's there. And so for the AR to try to map out the environment to be able to project AR, render AR information in the environment becomes a tougher problem.
Yeah. There's a second part to that. And then after I read this, I'm going to invite people to unmute themselves. I don't mind reading, but if you'd like, you can unmute yourself. The second part to that question, should transportation planners in rural communities or counties be looking at these technologies?
So I mean, so smaller towns, I think are less likely to have the kind of dense traffic that we used in this simulation. And so it's this particular, I don't know how relevant this particular study is to the sort of typical experience in rural and small towns. That said, rural environments are still dangerous for pedestrians in a lot of respects. People are walking along country roads, and particularly in the nighttime, country roads can be very dangerous. So I think there is value in people looking at applications of technology in rural environments. One of the things I showed earlier was, in fact, I can bring it up quickly here. So this is from a study we did for Toyota looking at, so here, this study here is a study of adaptive headlights. And adaptive headlights on vehicles have a separate set of headlights that can aim at pedestrians and illuminate them on the side of the road. They detect the pedestrians and then illuminate it for the driver. And then also it alerts the pedestrian to the oncoming vehicle. So that kind of technology in a rural environment, I think, has great potential. The AR technology, I don't see as much application for the AR technology in rural environments. The cell phone technology potential could have application in rural environments just to let people know when there are vehicles approaching and alert them to dangers.
I could, this study was about pedestrians, but I could see in-vehicle technology in rural environments, particularly divided highways. The same idea where are the safe gaps? And that would be a rural application for drivers in vehicles.
Yeah,
The
for
same
like
kind.
level crossings on
Mhm.
multi-lane
Yeah,
highway. Yeah, yeah, yeah. We have a lot of those.
yeah. In Missouri, they've instituted J turns where to turn left, you have to go down, make a U-turn, and then turn right,
Ah, yeah, yeah, yeah,
to eliminate that double crossing and the
yeah, yeah,
double, and so, and that's one of the technologies that won't necessarily work for pedestrians. I don't think it would work. It'd require them to walk farther. But those are some of the things that some infrastructure solutions to these kinds of things for vehicles.
yeah.
I don't want to get us off on
No,
tangent
that's great.
vehicles. Does anyone else have any questions?
I'm always happy to answer questions later. So I think, is my email posted somewhere, Don?
I don't have, is it in your last slide, or anywhere?
I did not put it in my last slide, but I'm easy to find. I'm just joe-kearney@uiowa.edu. So it's easy to find me. And if you have any questions, I'm happy to answer questions through email or
Thank
any
you.
other means of communication.
Thank you very much. Okay, and with that, I'm going to thank everyone for attending, and we'll see you next time.
Great, thanks a lot. Thanks for all the good questions.